I'm putting this video together to work through some of these Lewis dot structure polarity determinations. This all came from the first semester, so it's been a while. And we need to know Lewis dot structures and polarity in order to figure out what kind of IMF we're going to be seen in these compounds. So this is a worksheet that that was assigned as homework, and I'm hoping that this video will help you to work through some of this. I'm not going to do all of them, but I am going to pick and choose certain ones that I think maybe you should see and we can revisit. Okay? All right, so I just put together the first one, carbon tetrafluoride. Everything is there. I've got the Lewis dot structure here. I drew out the ball and stick structure so that you can see in 3 dimensions what we're looking at here as far as the structure of this compound. It's a tetrahedral structure because there's no one side of this molecule that's pulling electrons any harder than any other side of the molecule. Because of that, it is nonpolar. And if it's nonpolar, the only intermolecular force that this compound will experience is going to be the London dispersion force. Okay? Okay, here's the next one, boron trifluoride. Now, boron, if you remember from way back, boron is an exception to the octet rule that we talked about a long time ago. So boron is going to only have 3 chemical bonds. I drew out the spatial ball and stick model. I'm writing down the name of the shapes. I'm not going to test you on that right now, but keep this in mind. These names are going to come up on the semester exam. So I'm throwing it out there right now. This is trigonal planar. Nobody on this molecule is winning the battle for electrons, so no one side is going to have any more electrons than the other, so it's nonpolar, and we're going to see London dispersion forces at work here. Here is nitrogen trifluoride, and since nitrogen has this lone pair of electrons on the structure, that lone pair of electrons is going to take up space. And I highlighted in gray that there's a cloud of electrons that's pushing down on these molecules, creating a trigonal pyramidal structure. This is going to be a polar molecule because electrons are going to be pulled toward the fluorine. It's going to create a net negative on the bottom and a positive, a partial negative and a partial positive charge on the top and bottom. Okay, just like I've drawn there. It's because the electrons are being pulled to one side of the molecule that we've got polarity, and this is a dipole interaction because this molecule is a dipole. Di means 2. Pole means pole. It's got 2 poles, a positive pole and a negative pole. Okay, so here we've got this molecule. It's a trigonal planar molecule. If you're not sure why there's a double bond here, I'd really rather not spend this video talking about the intricacies of Lewis dot structures. I'd like you to maybe accept this. If you really need to, please go back to last semester's notes and see why that would be a double bond there. Anyhow, sulfur in this case it's got a relatively high electronegativity compared to the other atoms here. So there is going to be a pulling of electrons in this direction. Okay, so we're going to end up with a negative side and a positive side. It's going to be polar, and since it's a dipole molecule, there will be dipole-dipole interactions. Okay, with the carbonate ion, this is going to be a little bit unusual, okay? I'm not even defining what shape it is. By the way, it would be trigonal planar. But this structure here has a full 2 minus charge. I'm calling it a full charge because in this case up here, with these dipoles, we've got a partial negative, let's say, and a partial positive charge there. Okay, here we've got a full 2 minus charge. This is an ion, okay? It is going to exhibit ionic charge, okay? In other words, if I was to look at a compound, here's sodium carbonate, and I'm just coloring this in because it's fun. Okay, there, sodium carbonate. There would be a very strong pull here between the positive charged sodium ion and the two negatively charged carbonate ion, right? So there's a strong attraction here and a strong attraction there. This is a stronger attraction than a dipole-dipole attraction. This is a full positive charge and a full 2 minus charge and a full positive charge, not partial, okay? So again, very strong interaction between these ions, all right? Sodium carbonate, that's why it would exist as a solid, at room temperature. Sodium carbonate is washing soda, and we actually used it. It was one of the white powders that we used in the lab just recently. All right, so I said I wouldn't do all of these with you guys, but I am actually going to cut this video short, and I'm going to come back to page 24 in the next video. If you feel like you're good on this and you feel like you don't need to see any more, that's fine. Don't worry about it. Just then you don't need to watch the next video. I'm going to make the next video, I'm going to do all of the problems on page 24. I know I initially said I wouldn't do all of them, but I don't really see a problem with working through these. And if you feel like you need a little extra help, maybe watching this will help.